Are you excited about disasters? Yes. Because we all slow down to watch car accidents, and we all want to watch other people's disasters because it gives us both the warm feeling that it's not our disaster and the hope that we can avoid our own personal disasters. So I'm here to talk to you about Y2K. How many people remember working during Y2K? Oh, I love you. The few, the proud, the grizzled. This is a story about my friend who was a sysadmin. It was December 31st, 1999, and she had just bet her boss that their systems wouldn't go down. The stakes of this bet were her job. She was driving 4 hours away from Des Moines to Minneapolis to go to a New Year's Eve party because she was 20-something, and her boss said that if anything went down, she didn't need to bother coming back to work. So here's Chicago, yeah. Here's Des Moines, Minneapolis. I love this shot. It makes it look like it's all so close. Yeah. Although a lot of us get pages now, very few of us carry pagers anymore. This is what an actual pager used to look like. This is a very modern pager. You can tell because it isn't just, you have that very pager, yeah. And the pager works like this. You clip it on your belt until you drop it into the toilet, and then you get both a better belt and a new pager. When it goes off, you need to leave whatever it is that you're doing and go and call in on a payphone to find out what's gone wrong at work. So every time you went to a dance club, there would always be a disgruntled-looking person standing in the lobby like this, trying to talk into a payphone and say, "What went wrong? Uh-huh. No, I'll come in." Because remote administration was not really a thing in 2000. If anything went wrong, you had to go in and fix it with your actual fingers. So it didn't really matter that you had a pager and could call into work. You were always going to have to go in anyway. So our sysadmin had her pager, but if something went down in her system, she was 4 hours away across snowy Minnesota, Iowa roads. She wasn't going to make it back in time. And her boss told her that she didn't need to come back if anything went wrong, if anything went down. But she left anyway because she knew everything would be okay. This wasn't an act of faith on her part. It was because she had spent all of 1999 patching and testing her systems. And back then, patching and testing your systems involved actually calling people on the phone and getting them to send you a disk or a firmware update. And it involved sometimes actually splicing wires together out of the server closet because whatever it was you were updating didn't actually have a disk drive, and you had to like hack that together so you could update it. I tell you what, if Y2K were happening right now, all of our cables would be obsolete and we would be in really bad shape because HDMI has DRM in it and it checks the date. So we were really worried about Y2K, and when I give this talk to people who are younger, which is a lot of the industry that we're working with now, they sort of go, nothing bad happened. It couldn't have been that terrible. And it was. And we know it was because we spent a lot of time on it. And we spent all of this time testing. Things did go down because of Y2K, but they went down in July because that's when the utility was testing it. And because they were doing staggered testing, we didn't have the cascade failures that we were worried about. And things did go down. People did have war rooms. It was, in fact, a real problem. But we never think of it that way because we mitigated it. This was a really successful example of a disaster that didn't happen. As we get further from the reality of Y2K, we forget. We forget how many millions of dollars and person hours we spent on trying to figure out how to make this not a big deal. The SEC threatened to cut off non-compliant banks by the middle of 1998. Like, that's a lot of scramble. People who knew COBOL were working their fingers to the bone to make sure that we were not going to lose systems. And this massive distributed effort was almost invisible to the general public because they were worrying about things like their ATMs. We were worrying about things like air traffic control systems. Thousands of programmers were hired to remediate systems that couldn't be upgraded. We didn't have the idea of push upgrades. There was no way to send out a package that like automatically security updated anything. That wasn't how it worked. We were proud of how long we could have our servers up without rebooting them. Like years, right? You're like, yeah, my server's been up for 3 years. Rebooting was a sign of failure. And it turns out that if you leave a server up for long enough, rebooting it is also just like a way to kill it. Not every time, but once in a while. And so there was a series of failures, but it wasn't publicly visible. The space program, which we think of as this massive distributed effort, was a fraction of the work that we did to mitigate Y2K. Because it was big and shiny, because it had this amazing outcome that we could all point to and say, we put a person on the moon, we think of it as a big effort, but it was so much smaller than the Y2K remediation effort. The thing is, nobody remembers when we avert a crisis. It's easy for people who didn't live through it to say now that Y2K was overblown. Nothing really terrible happened. I don't think anybody really died of Y2K. So all of the people who had built compounds in Utah and Idaho and stockpiled food, they seemed silly. They wouldn't have seemed silly if we hadn't gotten it right. All of Y2K remediation was an exercise in risk reduction. We knew that there was something that could cause a problem, and we did everything that we could to prevent it. We do risk reduction in all sorts of places. We put anti-lock brakes on our cars so that we can stop suddenly when a child runs into the road in front of us or when we're on an icy surface. We do vaccination so that instead of getting measles and polio and chickenpox, we get an attenuated and non-contagious strain that challenges our immune system without making us sick. We have deer sirens that whistle so that deer do not leap out in front of our cars, hopefully. We have all of these things where, like, I would like the bad thing to not happen. So, what are the essential elements of reducing risk? How do we know what it is we need to prevent? It's impossible to avoid all risk. I'm going to say this over and over again because we keep reading about ways to reduce our risk on one vector and another, and we keep feeling like maybe it's possible to get our risk down to something tolerable. And the answer is, there is always a finite amount of risk that we cannot eliminate, and we have to make choices to balance it. For instance, we all know that statistics say it is far safer to fly than to drive to the airport to catch your flight. But we all still feel more in control of our lives when we're driving than when we're flying. So people will choose to drive distances that they could fly because it feels safer to them, even though that's not accurate. Rather than becoming overwhelmed at the idea of all the risk we deal with all the time, we have to break our world into zones and decide how much risk we can tolerate in each zone and secure it as much as possible. I'm a cyclist. I ride in the city in the winter in Minneapolis, and every year cyclists in Minnesota get hit and die. It's just a thing that happens. Sometimes they aren't visible, sometimes the driver is impaired or distracted. It just happens. And so I could either say it's not worth the risk to me, or I could say I accept that risk, I'm going to mitigate it the best ways I can. I wear bright clothing. I have an extensive light collection on my bike, so it's super reflective and visible. And I carry a lot of life insurance. So if I do get hit, my family's going to be okay. It's an acknowledged risk. I know it's dangerous, but it's an amount of dangerous I'm okay with. For another example of ways that we accept risk and mitigate it at the same time, I work directly on adding documentation to our APIs. There's a risk that I could break someone's integration if I add or delete something in the API. Like, I could seriously break a customer, right? But the way we address this is before I my code goes live, somebody checks it for me. Somebody says, no, actually, that's a weird thing that you put in there. It's going to break. This is a kind of risk mitigation that is so common we don't even think about it. Like peer review of code before we check something in. We don't really think about it as risk avoidance. We just think about it as good practice. Like, obviously, you wouldn't just want somebody checking things in willy-nilly with no second set of eyes. Pull requests and reviews are standard, and we don't think of them as risk reduction. But so are feature flags, development branches, test instances, and Canary deployments. They're all ways to reduce the risk. Another way to think about reducing risk is to predict the states that something can end up in. I am the English major, most likely to draw a little heart emoji next to a finite state machine because I think they are fascinating. I think they are amazing. What you're doing with a finite state machine is you're saying, this is the state of things as they are. Here are all the possible states it could end up in, and here are the transitions, how I got there. And once you can draw that out about a system, you can really understand where your likely breakage points are. I think that it's really difficult for us to think about using finite state machines as a tool in our daily lives because we're working with systems of such enormous complexity. But I think we can also maybe do a little bit about that to make it less complicated. The other side of risk reduction is harm mitigation. I teach junior high students sex ed. Harm mitigation says, I would rather you didn't engage in these activities because you're in junior high. But I acknowledge that because you are a teenager, some of you are going to anyway, so please don't be stupid. Here are some tools for not being stupid. The failure is going to happen, but I want it to be non-catastrophic. No matter how much we try to avoid risk, the truth is that bad things do happen. That's why we wear seatbelts and have life vests, and why we install smoke detectors and sprinkler systems and doors that swing outward. Ideally, we don't have house fires, but if we have house fires, we'd like to survive them. The most concrete real-world example of harm mitigation that I'm looking at right now is building codes. Building codes save lives, unequivocally. In 1985, an 8.0 earthquake destroyed Mexico City and killed at least 10,000 people. It was catastrophic. Since then, Mexico City has increased its population significantly, but they also started building for earthquakes, and they even installed an earthquake warning system that gives residents 10 to 15 seconds of notice when there's about to be a shake. It detects those low-frequency radio waves that dogs react to before earthquakes, and there's an alarm that goes off. It says, hey, there's about to be an earthquake. They shut down the elevators, and people go outside or to their safe rooms. 10 seconds is actually quite a lot of time to prepare for an earthquake. Last year, there was a 7.1 earthquake, not as bad as an 8.0, but still significant. So this is a major hospital in Mexico City in 1985. It's a well-built building for then. This is the worst picture of damage I could find from last year's earthquake. And it looks like the death toll in Mexico City is 228 people, rather than 10,000. And there are 25 million people living in Mexico City, and it is built on a partially filled lake bed that is the geographical equivalent of a bowl full of Jell-O. Once it starts shaking, it has resonances that keep it shaking long after the earthquake stops. Given all of these factors, the only mitigating change here was building codes. When they rebuilt after 1985, they made sure that buildings would not collapse. Another example of building codes is a negative one. In the US, we have had many memorable fire disasters that are seared into our cultural memory. When you see a picture of bodies in front of blocked, chained exits, like at the Triangle Shirtwaist Factory, it makes an impression. When we see pictures of the ghost ship Makerspace, we remember that people died, 28 people died, because they couldn't find the exit. They couldn't get out. It's why if a fire alarm right now went off, every door between here and outside opens outward and has crash bars. You don't need to open any handles. You don't need to turn anything. If a press of bodies goes up against that door, it will open, and doors will continue to open until you are outside and safe. It's a standard US building code that you never even think about anymore. I'm always thrown off when I go to other countries and they don't have this. And I'm like, what do you mean the door opens inward while I'm trying to go into the conference center? It's very confusing for me. The UK hasn't had the same kind of trauma about this. This is Grenfell Tower. It's a 24-story residential building, and it had a cladding put on it recently that obviated the existing fireproofness of the concrete block building and created a chimney that wicked flames up the entire side of the building and popped them into windows. And as a bonus, the cladding outgassed cyanide. We do not know and may never know how many people died in this fire because there were no sprinklers and there was only one egress stair in the center of the building, and it was blocked. It had old refrigerators and mop buckets and crap in it in a way that would make our little American souls just die. Like, you don't think about it, but you notice when an egress stair is blocked, and you kind of move things out of the way. So that's kind of a problem. Like, people died because of building codes, and you can tell that it was not just this cladding that was the problem, because this is the unfortunately named Torch Tower in Dubai. It had the same kind of cladding, and it had 79 stories, and there were no deaths or injuries. Nobody died. 79 stories. Everybody got out because there were clear fire exits at every corner. Everybody had a way to get out. That is such a clear evidence to me that thinking about the fact that high-rises catch on fire is a way to prevent people from dying, because we could do something about it. Chicago actually has some pretty draconian high-rise sprinkler system rules. And building owners kind of complain about it because it's expensive to put in sprinklers, and if they go off accidentally, there's a lot of property damage. But you know what? High-rise buildings with sprinklers have a 2% risk of fire spreading from floor to floor. It's just not going to happen. The sprinkler may go off, your stuff may get ruined, but you're not going to end up an uncountable casualty. So how do we mitigate harm? How do we make it so that things aren't that bad? The first step has to be acknowledging that we can never eliminate all risk. We'd love to believe that we could keep our children safe. We'd love to believe that we are the best drivers on the road. But that doesn't matter what we believe. What matters is what actually happens. And once we accept that there's risk in everything we do, we can identify it and figure out ways to ease the results. So you have to assume failure. If you don't know how your product is likely to fail, you're missing something. Failure modes may have different severity for some people. Like, if you have software as a service, a glitch in how you deliver the pages may mean people are a little irritated, or it may mean you just lost Black Friday. Like, what is the severity of something going wrong? Assuming it's going to go wrong is the first step to understanding that, and then figuring out how bad something is the next step. So for example, if my spouse reads my chat logs, she will find it funny and laugh. If someone with an abusive spouse has their chat logs read, they may die. So when you're thinking about how to predict these things, you need to not think like a comfortable technology person. You need to think like somebody who's marginalized, who's at risk already. And if you can't do that, hire somebody who can. Because It's very hard for us to understand other mindsets. Testers. Hire some testers. I know that this has sort of gone out of fashion and we're doing a lot of automated testing, but testers are people who never believe anything is going to go right. This is their superpower. They see the potential for things to go wrong and they try and make it happen. And if you don't have a couple testers on your team, at least for a while, you're never going to understand how badly things can get screwed up. When you're trying to decide whether a failure is catastrophic, you need to decide if you're going to fail safe or fail secure. Fail safe is usually used in terms of human life. For example, nuclear power plants, if they lack positive control, even for a moment, the control rods slam down and the reaction stops. And it takes a while to get it restarted and it's kind of a pain in the ass. But you don't melt down. And almost all nuclear accidents that happen have happened because something in the fail-safe has gone wonky. We don't understand enough about what's going on. So when we're protecting human life, we try to fail safe. But sometimes we want to fail secure. Who here has worked in a server room with halon fire extinguishers, right? And did it scare you?
Yes.
Yeah. No. Did you have masks on the inside of the room? This is why you're scared and you're not, yeah. Like, probably there's not going to be a fire, and probably even if there was a fire, somebody wouldn't be in the room when it happened, but we would like to not kill people if they happen to be in the server room when there's a fire. We are protecting people and property, hopefully, at the same time. Another example of this is laptop computers. I worked at Microsoft on the very first version of BitLocker, and what we realized was hardware is meaningless. Hardware is replaceable and cheap and easy. Access is a vulnerability. So we would rather wipe out everything that is in your hard drive and make it completely inaccessible to you or anyone else, rather than let a bad actor have access to your credentials. That's a pretty radical shift in how we think about things. To say data exists in the cloud and is important and should be protected, hardware is meaningless. So when we say we're failing secure, what we're saying is, like, you may lose some stuff, but the company is going to be safer. Disasters or catastrophes aren't the result of a single failure. Instead, they're a collection of small failures in the systems of safety that protect us most of the time. It doesn't matter if you put the lid on your travel mug wrong, as long as you don't drop it, right? Like, there are 1,000 times you've done something a little half-assed, and it didn't matter because nothing went wrong. It only matters when something goes wrong that these systems of safety have also failed. Why is it hard to predict failure states? Because despite my simplistic examples, failures are multi-layered. Even though we think we've designed for redundancy and failure, our systems are so complex that we have a terrible time understanding how all the interactions work. We saw this when LinkedIn managed to turn on every single feature flag that they had simultaneously, rendering their site completely unusable. It's not that anybody ever said, let's do that. That seems like a great idea. It's that there wasn't a check to make sure that didn't happen. When you're building a system, we would like to think about testing it all the time, because that's how we prevent both failure and lack of function. And when you think about a system that's full of microservices, I sort of think of it like Tinker Toys. You can test all of the round things, they don't fail, that's the microservices. You can test all of the sticks, they don't fail, those are the communication channels. The failure only happens when you combine these together into some kind of unit. It only happens when you put the system under pressure. So we can't ever say, I fully tested something just because of unit tests. Only integrate, like, you need to do the unit test. You have to tell that the hubs and spokes are going to fit together. But integration testing is the only way to tell that you're actually testing something properly. Now that we have microservices, we have to pay attention to these internal channels and crosstalk in a way we haven't had to track external channels. Multiplying combinations of microservices and channels grow quickly. This is the orbit of Mars and Venus over the course of a year. That's 2 points orbiting a single fixed point, which is, by the way, not fixed. And that's just like, those are just the combinations for that. Now think about how much more complex it is when you're talking about dozens and dozens of microservices. It's a huge array of observations that we can only hope are predictable, but probably aren't. So what can you do about it? The easiest path for this in software is the kill switch. We used to do this process by redeploying a known good build, but that's really painfully slow when you're in the middle of an emergency. And so I want to say to all of you, consider how it is you can turn off a badly behaving microservice in a real hurry. If you have a transition state in your finite state machine of kill the process, that stops it from spiraling out of control. It's the SAS equivalent of a cat falling off a bed and then walking away with enormous dignity. Like, oh, that went wrong. Turned it off. Everything's fine now. Good to go. Yep. So I keep talking about disasters, and I think I'm going to back up and explain what a disaster is. Every disaster that you can think of, from natural disasters like hurricanes to engineering disasters, has several contributory factors. High winds and storm surge are fine until they knock out power or take off roofs and let the rain in, and then people are exposed. And exposed people may survive, but they still need food and water and medical care, and if you've lost the roads, it's hard to get that to them. I have a whole nother talk called Waterhouse Resiliency about how it is that we can plan for natural disasters and have things in place for when things go wrong. But let's take a look at how failures chain together into a disaster. This is the 35W bridge in Minneapolis, except it's not. This bridge, one beautiful spring day, fell into the river. 13 people died, and that was a miraculously low number because the bridge was mostly to partially closed for construction. And we couldn't figure out why the bridge had suddenly fallen into the water. It was pretty startling. It turned out, when we fished all the pieces out and put them together, the primary cause of the collapse was the undersized gusset plates at 0.5 inches thick. Contributing to that design or construction error was the fact that 2 inches of concrete had been added to the road surface over the years, increasing the static load by 20%. Another factor was the extraordinary weight of construction equipment and materiel resting on the bridge just above its weakest point at the time of collapse. That load was estimated at 578,000 pounds, about 262 tons, consisting of sand, water, and vehicles. The NTSB determined that corrosion was not a significant factor, but that inspectors did not routinely check that safety features were functional. That's the Army Corps of Engineers report on why it fell into the water. They spent 18 months figuring that out. They found out that the trusses were half as thick as they should have been, according to the design specifications. But that had been working okay for 50 years, since 1965 when this bridge was built. The bridge was millions of pounds heavier than it was designed to be. That had been working okay. There was a little corrosion in the bolts and trusses. That was working okay. There was construction weight and movement. We'd had 3 major resurfacings of this bridge. That had been okay. All of these factors together caused the bridge to collapse in 2007 because it was all of those factors that fatally weakened it. When we fish our own disasters out of the river and piece them back together, we find out that it's the same. The cluster had a bad shard, but that didn't matter until this and that and the other thing went wrong, and we threw a bunch of traffic at that cluster, and the bad shard had to take more weight than it could bear, and then it went down, and then it took the cluster down, and then, oh, there was an outage. We have to give Netflix credit for popularizing and toolifying an interesting way to head off disaster. Their chaos monkey concept tests services by taking them out randomly. And the idea is you set it off, and then if you notice a degradation of service, you don't have enough resiliency to have that kind of level of disaster. If this creative breakage seems terrifying to you, you probably don't have enough resiliency in your system. So here are some general concepts to investigate that are going to, I'm going to go into them pretty fast. How am I doing on time? 10 minutes, perfect. So here are things that create fizzle out of things that could be disasters. How do we make disasters really boring to talk about and something that doesn't happen, right? Microservices and loose coupling. Not pets, not cattle, bacteria. I want these things to auto-generate themselves. I want them to spin up themselves because we need to think of systems as separate from their components, and we need to think of the components as disposable. So when you think about you, you don't think about the fact that you're constantly shedding skin cells. When you think about your system, I don't want you to care that your microservices are going up and down all the time because there's always enough to keep sustaining life. One of the common mistakes we make in mitigation is that systems can't always talk to each other smoothly, or if there's a problem, it takes out the messaging too. So make sure that your danger signals use a different pathway than the system they're signaling about. So I think the most painful example of this was when S3 went down, but we couldn't see it on the status page because the icon was in S3. I'm like, that's like a classic example of, is my site down or not? Have a status page that somebody else is hosting. Because otherwise, when your status page is out and your everything is out, nobody can tell what's going on, and they just keep calling support to say, hey, did you know you're down? We know we're down, thank you. Data duplication. Data storage is cheap, so make sure you have it in more than one place. And I always pick on Delta at this point. I'm a happy Delta customer, but I'm mad at them about this one thing. When they acquired Northwest Airlines, they shut down the perfectly functional Northwest Airlines data center in Minneapolis, which was fine until their data center in Atlanta caught fire. Because who expects their data center to catch fire? Well, nobody, but it did. And then they had like 3 days of nightmarish outages and extremely expensive remediation because airplanes don't work without computers anymore. So if they had kept a duplicate data center up, it might have cost them money, and they might never have had a disaster, and they would have failed over during the fire, and we would still be having arguments at their upper levels about whether or not something was worth keeping 2 data centers for. So if you're having that argument, think about what happens if one of them catches fire. Canary launches. I want you to be able to test your feature in production because no matter how good you are at scripting, you're just not going to be able to send through the weirdness and intense traffic of a Black Friday to your test server. It is expensive and hard and almost unbelievably difficult to match your production environment in test. Who here has an all-up test environment that's exactly like production? Right. You do? Good for you. You have a lot of money. Or you're very small. Or a small production environment. But what I'm saying is you're going to have to be able to test in production. And the way to do that is to do some kind of dark launching to put things out in production and test them without your users seeing them. And obviously I work for a company that makes the product that does that, but you can do it yourselves. There are ways to do it. But you need to be doing it. You need to be testing in production all the time. That has to be your final acceptance. Not test, not staging, test in production. Kill switches and circuit breakers. Humans are the slow meat part of any system, and if there is something going wrong, I don't want to have to wait for a human to react to it. Computers are good at fast reactions. They're good at having a threshold and reacting to it. So, although humans are a great design for preventing cascade failure if you need to stop a runaway process, we're terrible at preventing a cascade failure if what needs to happen is things do need to stop because it takes us a while to get online. Circuit breakers can detect anomalous activity and respond to it much faster than we can. And that gives us time to catch up and find out what's going on. If you have a run book for how to get a system back up, you've automated it, right? Because if a system goes down and you know what's going to happen to get it back up, why don't you just have a script to run that? Because I'd love to tell you that technology is perfect, but I'm pretty sure technology is a cranky toddler, and sometimes it just needs a nap. And you stand it back up and it works fine. And you have no idea why it went down, but it just needed a nap, that's all. It reset itself, it's fine. If it goes down again, you should absolutely page somebody at 3 a.m. to figure out what's causing a problem. Sometimes it just needs its logs purged. It's like the 2 a.m. diaper change equivalent. And so automate, at least once, standing your system back up before you start to get people involved. Because again, we're the slow meat-based portion of any system. You can't test modern software fully in a test environment. I already said this part. Do your unit and integration test, yes. But test for load and stress and outage. Before we had cloud computing, I had a fantasy where I was going to have a semi full of computers that would just travel around to different crafting shows and do their 1 day of registration. Because they only needed this burst of computing 2 or 3 days a year. But they really, really needed it. It was like being slash-dotted by grandmothers. It's this small site that didn't have that much requirement during the year, but then like 4,000 people wanted to register for 18 classes each, and they all had fixed seat limits, and they would just hammer this site over and over again. And the site would then go down, and then people didn't know if their registrations had worked, and it was all this nightmarish thing. And of course, nobody would take seriously people who are like, no, you don't understand. These grandmothers are super intense about their knitting, and they will be very angry if we go down. So this concept of surge protection is something that you need to build into your testing. Don't test for the good day, test for the catastrophically busy day. Because if you don't test under load, you will fail under load. So if this talk was too long and you read Twitter instead, here's the quick takeaway. Expect things to fail. Make your systems less rigid and more flexible. Plan and practice for disasters because they're going to happen. Degrade gracefully. Make sure that when your systems don't go down, it's not an all or nothing thing. Give people a chance to have like a partial part of the web page. Like keep your catalog page up, but take away the shiny, flashy interface, okay? That's fine. Degrade your systems before you turn them off. You can only do that if you understand what parts are disposable and you plan to jettison them automatically when you start to have load problems. So I have been sent here by the grace of my employer, LaunchDarkly. We do feature flags as a service. We have a booth upstairs if you would like to, or downstairs, if you'd like to go talk to us. And if you would like a free t-shirt, you can take a picture of this URL and go visit it, and we will send you one. Thank you for your time.